Here we go. Who's my favorite student? Oh, good old Anne. A motor is connected to 240 volts, so they've given me an EMF, a voltage, draws 30 amps when it's prevented from turning. Ooh, I think this is going to be a back EMF question. At its normal operating speed, the motor draws current of 3.2 amps. The first thing they want is the resistance of the armature coil. So we said this. I can't remember which version I gave you on your formula sheet, but I know that the source voltage minus the back voltage leaves me the voltage left over in the coil. And if I'm prevented from turning, I know that that equals 0. So the source voltage is 240 volt. Well, you know what? Let's do this a bit more algebraically. I then get this, which Declan is really just Ohm's law in disguise. It's V equals I times R, but I'm using the EMF symbol because in some of our equations we have a lowercase v and it gets confusing. They want the resistance. R is going to be the source, 240, divided by the current when it's not turning, 30. I think I can do that in my head. R is it 8 ohms? Is that correct? If you got that, 3 out of 3. Otherwise, I would probably give you 1 mark if I saw that, 1 mark for that, and 1 mark for the answer. What's the back EMF at normal operating speed? So again, for any electric motor, the source is what supplies the voltage, but as soon as it starts to turn, it sends a back voltage in the opposite direction, and whatever's left over is left to make the motor accelerate, is left to make the motor speed up. I want the back EMF. Gonna do a swappy dance. The EMF minus I times R, that equals the back voltage. What's the source voltage? 240 minus, what's the current when we're turning? 3.2. What's the resistance? That's why I had to do part A first when it wasn't turning to figure out the resistance. I'm going to get 240 minus 3.2 times 8. 240, Mr. Dueck, where's the 4? Minus 3.2 times 8. 214.4, I'll call it 214 volts. What's the net voltage left over? Whatever 3.2 times 8 is. There's my I times R. As the motor speeds up more and more and more and more, the back voltage ideally matches the source voltage. Then you have no net current running through your motor. That's when it runs its coolest because power loss or heat is I squared R. An ideal step-up transformer's primary coil has 50 turns. Its secondary coil has 1,500 turns. Okay, here's my pair. So I already know I'm going to be using N primary over N secondary. Oh, and then they gave me V primary, and they want V secondary. They want that. I don't know how good you are at cross multiplying, but if you want a real shortcut when you have one fraction equals one fraction, V secondary is going to be that times that divided by that. If you imagine a little x, it's the two things that you know divided by the one diagonally from what you're trying to find. That always works as well. That's really rewriting fractions quickly. However way you want to get the VS by itself, it's going to be that. So it's going to be secondary 1,500. Primary voltage 120 divided by primary turns 50. 1,500 times 120 divided by 50. 3,600, is that correct? I see people giving me a thumbs up. I see Bishon giving me a thumbs up. Always nice to see Bishon do the homework. And that's going to be volts. If you got that right, 2 out of 2. Otherwise, I would probably go 1 mark for that, half mark for getting the V by itself, and a half mark for the answer. Actually, I'd probably go half mark for the numbers, and I'd probably just go a half mark for writing this down, since it's kind of 4 steps. What's the primary current? So again, I'm going to use N primary over N secondary. I could use my voltages, but just in case I got them wrong, why bother? Current doesn't match. It's going to be secondary on top, primary on the bottom. And they want me to get this one by itself. Okay, the primary current is going to be the secondary number of coils times the secondary current divided by the primary number of coils. It's going to be the secondary number of coils times the secondary current divided by the primary number of coils. I think I can do that in my head, can't I? 1500, 90? No, 900? 90. 90? 90? Yes? If you got that, 2 out of 2. Otherwise, again, half mark for that, half mark for that, half mark for that, half mark for the answer. Did I ask whether this is a step up or step down? No, I didn't. Is this a step up or a step down transformer? Because, again, step up increases the voltage. It lowered the current. The step up? Yeah. Lowered the current from 90 down to 3. A coil of wire is moved into a magnetic field as shown below. What's the direction? Evan, this is the ones I've been talking to a number of you about. If it's a before and after diagram, it's a lot easier because I can just say, what's the after magnetic field? It will oppose it. Here, where we're going from no magnetic field into a magnetic field, or if we're going, like in the next question, from, oh, here's the before and after. This one will be easier. Here, what I tend to do is I imagine the coil halfway, right there. Half of it is in, half of it is out. And I look at the section that's in, and I put a proton on the front of it. What direction is that proton traveling? To the right. What direction is the magnetic field? Into the page. This proton is going to feel a force downwards, which means the current is going to be, as it enters, going in that direction. Is that clockwise or counterclockwise? That is anti-clockwise. Pause for a second. These ones I find easier where there's a clear before and an after. I just look at the after. What direction is the magnetic field in the after? Out of the page, this coil is going to oppose that. This coil is going to act into the page, which in my situation is clockwise? Yes? Clockwise. 1 mark. If the constant magnetic field strength is 1.2 Teslas, what's the magnetic flux? 2 marks. So this is just asking, do you realize that flux equals BA? This is not a changing flux. No current will be induced in this situation. B is 1.2. A, what shape is this? Rectangle, which is just going to be length times width. It's going to be 0.08 times 0.12. Oh, got to pause the video again for a second. Hang on a second. Continuing on, so there it is, magnetic field times area. If it's a circle, the area is pi r squared. Rectangle or square, it's length times width. So it's going to be whatever this is. It's going to be 0.12, no, 1.2, I said 0.12, 1.2 times 0.08 times 0.12, 0.01152, 0.0115 Webers. If you add the 2, that's fine. I just went to my usual 3 sig figs. I would give you 1 mark for that, half mark for the numbers, half mark for the answers. No units, wrong units, I'm taking a half mark off. Ooh, what's the induced EMF? Nothing. Why 0? No changing flex. It specifically said constant magnetic field strength. You're not going to induce a current. This was what stymied physicists for so long. They were, why aren't we getting a current? We're setting everything. It's when the flux is changing. This was Faraday's aha. You need a changing magnetic field or a changing area, but it's much easier to change the magnetic field. The magnetic flux through a circular coil. Oh, now we have a circular coil, and they did give me a radius, not a diameter. What's the strength of the magnetic field? So flux equals B times A. I guess the magnetic field is going to be the flux divided by the area. It's going to be 0.015 divided by pi r squared. The magnetic field strength is going to be 0.015 divided by bracket pi times 0.075. Don't forget the squared. I've had some of you ask, you only square the r, not the pi. It's pi times r squared, not pi squared, r squared. Magnetic, pretty strong magnetic field, 0.849 Teslas. Is that correct? Yes? People nodding? Okay. 2 marks for that. Half mark for the equation, half mark for rewriting it, half mark for the numbers, half mark for the answer, but if you got it right, 2 out of 2. The metal strip below is 25 centimeters, 0.25 meters, moving at 8.9 meters per second. The external magnetic field is 1.2 Teslas. The resistance is 0.0, so there's a resistor. So this is going to be a complete circuit, whichever way this current is going, I don't know yet, but this is going to be a complete circuit. First, it says find the induced EMF. This is a bar, not a coil. I'm going to use the induced EMF equals BLV. It's going to be 1.2 Teslas, very strong magnetic field. It's going to be a length of 0.25, and it's going to have a speed of 8.9 meters per second. 1.2 times 0.25 times 8.9. I get 2.67 volts. Is that correct? Anybody else? People nodding? Again, I would give you probably 1 mark for that. Half mark for the numbers, half mark for the answer. You can do this using Faraday's law by treating that space as a changing area. It's doable. Why bother? Use BLV. Find the current running through the circuit. So I guess the current is going to be the voltage divided by the resistance, because V equals I times R. It's going to be 2.67 divided by, what was the resistance? 0.025. 107 amps, is that right? I see a nod. 106.8 or 107 amps. 1 mark for that, half mark for the numbers, half mark for the answer. Find the magnetic force on the strip, magnitude and direction. Okay, so where is the magnetic force coming from? Well, as soon as we start to move this, we have a proton moving in this direction, to the right. Everybody point your right thumbs to the right. Which way is the magnetic field? Out of the page. This proton is going to feel a force downwards. So now, not only are the protons moving right, they're moving down. Right-hand rule again. Point your thumbs down the page, magnetic field into the page. You're going to feel a force to the left. You will feel a force resisting. Of course you will. That's what Lenz's law says you're always going to feel. You're never going to feel it going with you. You're always going to feel it against you. If I was pulling this thing that direction, I assure you the force would be in the opposite direction. So first of all, for the direction, I can already answer that. It's going to be left. What's the magnetic force on a wire? Hey, that's from last unit. That's Bill. What was the magnetic field strength, Mr. Dueck? It was fairly strong, wasn't it? 1.2 Teslas. I is 106.8. L was point something, 0.25. How many newtons of force? 1.2 times 106.8 times 0.25. 32.04, I'll call it 32 newtons, is that correct? And now I'll put in the direction next to my answer, at left. You don't have to put the at symbol, to the left. So I would give you 1 mark for the direction. I would give you a half mark for Bill, a half mark for the numbers, and a half mark for the answer. No, 1 mark for the answer, Mr. Dueck. Before you turn the page or before you shut your brain down, follow-up questions I could ask. What's the back EMF? I could ask that. What's the voltage? Now that these are moving down the page, I could ask, what's my net current? I could ask also, we could ask our maximum speed. That's when the source voltage equals the induced voltage, when the source current equals the back current. All sorts of other questions. We did a bunch of those in the homework. Can you give yourself a lovely score, please, out of 25? If you need to lawyer with me, now is the time. Otherwise, if you could pass them inwards, and the person in the middle, put them in a nice neat stack, all facing the same way.